My name is Danilo, and today we will talk about fresh text-to-image synthesis model, Stable Diffusion XL, which release of which was accompanied with corresponding paper, Sdxl, and proven latent diffusion models for high-resolution image synthesis. So the last year brought enormous leaps in deep generative modeling across various data domains such as natural language, audio, and of course vision. One of the vision models was Stable Diffusion XL, why we are gathering today. A bit of background, released in August 2022 by Stability AI, Stable Diffusion version 1.4 model is considered to be the first publicly available Stable Diffusion model. Currently, there are several models available, from 1.1 to 1.5 Stable Diffusion first version, 2.0 and 2.1 Stable Diffusion, and also new ones, Stable Diffusion XL 0.9 and Stable Diffusion XL1. And with release of every model, the quality becomes better and better, and loyal community also participant to increase it even more with fine-tuning, while reducing the usage of VRAM. So Stable Diffusion XL is the latest version of Latent Diffusion Model for text-to-image synthesis, which was released in two parts, base model and refinement. Both models are open source, so as the previous Stable Diffusion model, which is pretty good. Stable Diffusion XL is the first Stable Diffusion model designed for generation in image with 124 squared pixel size versus 512 in Stable Diffusion 1 and 768 in Stable Diffusion 2.1. So for a long time, Stable Diffusion 1.5 was a favorite among users. So even after the release of 2.1. So when a new player appeared, users were a bit skeptical. They feared that the situation with Stable Diffusion 2.1 will repeat. But Stable Diffusion XL, it has shown its superiority compared to previous models, and now the CVTI model side is teaming with fine-tuned and personalized Stable Diffusion XL models. So let's see what contributed to such significant improvements. Basically, Latent Diffusion model pipeline, it's the same among all models. It consists of three main parts: text encoder, text conditioned UNet, and variational autoencoder. And so what's new in Stable Diffusion XL? Basically, all components were doubled. There are now two text encoders, and therefore we may use two different pairs of prompts. And also there are two UNet models, base and refiner, and a single variational autoencoder, but it's improved too. So let's discuss each component individually and see what's new in Stable Diffusion XL. The first step in the pipeline is text encoding, given positive and negative prompts. They are encoded into text embeddings, concatenated, and feed to UNet module. So the authors used two text encoders, OpenClip combination with clip. OpenClip, clip with L was also used in previous Stable Diffusion version 1 model. The text encoders have total size of 870 million parameters. So as I said earlier, we can use two pairs of prompts for each text encoder, or we can just use a single negative and positive prompt and just don't bother yourself. Okay, let's recall the concept of diffusion models. Diffusion process unfolds in two distinctive phases. In the first part, we take an image and introduce a controlled amount of Gaussian noise step by step. Amount of those steps in Stable Diffusion it's about 1,000. So this first step is referred as forward diffusion. And in the second part, we aim to denoise the image and reconstruct the original content using denoising UNet, and this process is known as reverse diffusion. So while diffusion models have achieved the state-of-the-art results in its estimation as well as in sample quality, evaluating and optimizing these models in pixel space has the downside of low inference speed and very high training costs. Hereby, Latent Diffusion Model is designed to tackle this problem. As its name points, the diffusion process happens in the latent space, and this is what makes latent diffusion models much faster than pure diffusion models. So for this purpose, the autoencoder is trained. We use encoder to put the pixel space image into latent space. In the latent space, the diffusion process is done, and then those latents are get back to a pixel space using a decoder. And the true power of Stable Diffusion Model is that it can generate images from text prompts, and actually it can also use another data like another images, but it's a whole another story. So this is done by modifying the inner diffusion model to accept conditioning inputs. So here you can see the UNet model inside the Stable Diffusion. And remember this image, we'll come back to it later. What is new in Stable Diffusion XL UNet is that in Stable Diffusion XL, we used a heterogeneous distribution of transformer blocks. For efficiency reason, the transformer block at the highest feature level was omitted. The second and third level was set to 2 and 10 blocks. And the lowest level was just removed. Also, Stable Diffusion XL enhances its model capacity by incorporating a large number of UNet parameters, allowing for more sophisticated image generation. For example, Stable Diffusion version 1 used 870 parameters. Stable Diffusion 2 used 875 parameters. Millions, of course, millions. And Stable Diffusion XL uses 2.7 billion parameters. What else new in UNet structure is that the authors added micro-conditioning, several micro-conditionings. Let's discuss each of them. A notorious shortcoming of the LDM paradigm is that fact that training a model requires a minimal image size. And the two main approaches to tackle this problem is the first, just discard all the images that are below our threshold, which can lead to a significant portion of the training data will be discarded, that will lead to a loss of in performance and herd generalization. For example, the authors research their data set, and they understood that if they just discard the images below 256 threshold, they will lose about 40% of data, which is pretty much. Another approach to deal with the problem is to upscale images that are too small, but that may lead to leak upscaling artifacts into the final model output, causing, for example, blurry samples. So what did the authors propose? Instead of those approaches, they proposed condition the UNet model on the original image size, image resolution, which is trivially available during training. In particular, they provide the original height and width before rescaling of the images as additional conditioning to the model C size. Then each component of the image is independently embedded using a Fourier feature encoding, and those encodings are concatenated into a single vector that we feed into the model by adding it to the time step embedding, which we saw in UNet structure. So basically, the authors provided another NLP feature into the diffusion model, positional encoding based on learnable Fourier features. And the idea of this conditioning is that we basically tell Stable Diffusion XL to generate, for example, 248 image that looks like it was downsampled to 124, 184. So at inference time, a user can set the desired apparent resolution of the image via size conditioning. Here is a small example of this size conditioning, of impact of size conditioning on the image quality. So they picked 4 different values for size conditioning, and we may see that it's improved the image quality dramatically. Also, the common problem in the previous Stable Diffusion models is that they may cut a central object from the picture, like, for example, the first 2 rows where cat's head were cut from the output image. So what did the author propose? They propose another conditioning. So basically, they provide they uniformly sample crop coordinates C top and C left, where C top is the amount of pixels that were cut from the top, and C left is the amount of pixels that were cut from the left, and feed them into the model as conditioning parameters via Fourier feature embeddings like in the previous example. They concatenated those embeddings with another tool, time step and size conditioning, and just feed it to UNet structure, to UNet. So large-scale datasets are on average object-centric. So we can set, for example, ctop and cleft as 0, 0 during inference, and thereby obtain object-centered samples from the trained model. Also, we can tune those values to simulate the amount of cropping during inference. And this is a form of conditioning augmentation. So from the image, we can see that setting crop to 0, 0, we may get a nice object-centered image using the value 0 to 156. We can see that it wasn't cropped at the top of generated image, but it was cropped from the left side of the image. So the benefit of this approach is that while we make sure that those crops doesn't leak into the generation process, we actually can use it to our advantage to gain more control over the image synthesis process. And another feature that the authors added, real-world data sets include images of widely varying sizes and aspect ratios, while the common output resolution of text-to-image models is squared. It's 512 or 512, 512, or 124, 124, which is rather unnatural choice given the widespread distribution and use of landscape or portrait format screens. So motivated by this, the authors fine-tuned the model to handle multiple aspect ratios simultaneously. The idea was they partitioned the data into buckets of different aspect ratios, where the pixel count were kept as close to 124 squared pixels as possible, varying height and width accordingly in multiplies of 64. And during fine-tuning, training batch is composed of images from the same bucket. And for each training step, they alternated between the bucket sizes. Additionally, the model receives the bucket size as conditioning, represented as a tuple of integers CAR, which are embedded into a Fourier space. In practice, multi-aspect training were applied as a fine-tuning again stage after pretraining the model at a fixed aspect ratio and resolution, and it was combined with the conditioning techniques from the two previous slides. So here is a small cheat sheet of native Stable Diffusion XL aspect ratios, which it can handle. Also, Stable Diffusion XL presented a new autoencoder. The autoencoder architecture is the same as in the original Stable Diffusion version 1, but with a much larger batch size, and also weight tracking using an exponential moving average. Stable Diffusion 2 uses an improved version of Stable Diffusion 1's autoencoder, where the decoder was fine-tuned with a reduced weight on the perception loss. So XL's version of the encoder, it's much better than in Stable Diffusion 1, and a little bit better than Stable Diffusion 2. And the final model of our pipeline, it's Refiner. Refiner is trained in the same latent space as base model, which is specialized on high quality, high resolution data, and employ a noise in the noising process as introduced by Sdedit on the samples from the base model. Refinement model specialized on the first 200 noise scales. So the idea behind the refiner is that we don't need this whole process of noising from 0 to 1,000 steps. We may use just first 200 to train a model to fine-tune, to improve quality of the image. So refiner gets on input the latent from base model, which is already have good quality, so we don't need to reconstruct it fully. We need to only improve it a bit. You can see here on the picture the refiner performance. On the left, it was its base image, and on the right, it's a refined image. We can see that refiner added some details to water. It improved skyscrapers quality, but actually refiner is not. It's optional, so we may just not use it and save a bit of time. And another example, here the refiner impact bigger than in the previous figure. We can see that it improved face quality, added some details, deblurred to be specific, this man's neck, and did something with plates. It's all right, I guess, before refining too. So now with all this information, we can return to Sdxl pipeline and discuss its data flow. So using positive and negative prompts, or two pairs of positive and negative prompts, we feed it to text encoders, then concatenate those embeddings into a single text embedding and feed it to base model, which makes its magic and returns 128 latents, which can be either fed forward to refiner, or it's not shown in the figure. It can be directly fed to variation of the encoder and to be decoded to pixel space into our output base image. Or again, we can feed it to refiner, improve image details, again decode this latents into pixel space and get our refined image. So finally, some demonstrations. The authors decided to check the Sdxl performance by comparing the results of Sdxl with state-of-the-art text-to-image generation model Midjourney. As the source for image captions, they used the PaTI prompts benchmark. So 5 random prompts from each category were chosen, and 124 images were generated by both Midjourney and Sdxl for each prompt. The images then were presented to 17 100,000 members of AWS ground truth task force who voted based on adherence to the prompt. And most of the members, about 55%, voted for Stable Diffusion XL, which is a pretty good design result. Also, the authors did another research. Each prompt from the party prompts benchmark is organized into a category and a challenge. And each focus on different difficult aspects of the generation process. And we can see that in category benchmark, users mostly prefer Stable Diffusion XL. By the way, Stable Diffusion is blue. I forgot to mention it. Yeah, they mostly preferred Stable Diffusion XL. And in challenge benchmark, the users either preferred Stable Diffusion XL, or the results were almost equal from Stable Diffusion and Midjourney, or in 3 categories, they preferred Midjourney more. So let's compare the images of Stable Diffusion XL with another models. At first, we compare it with its previous versions, 1.5 and 2.1. Again, it's all subjective, but in my opinion, XL results are more closer to a prompt, and the quality is better too, at least in case of capybaras. Also, we can see that Stable Diffusion XL handles text generation much better than its previous versions. Here is kangaroo with this sign. Also, the authors compared XL with another third-party text-to-image models, Deploy, DALL-E, Bing Image Creator, Midjourney. Again, it's all subjective, so I just show you those images, and you decide what model you like more. Again, a small amount of text all models handle pretty well, like 7, except for Midjourney for some reasons, but okay. And conclusion. Stable Diffusion XL, it's not perfect. It's not perfect at all. It has a lot of drawbacks. As the previous models, Stable Diffusion XL may encounter challenges when synthesizing intricate structures such as human hands. It can be seen on the image in the first row. While the model achieves a remarkable level of realism, it's still not perfect photorealism. Also, in certain cases where samples contain multiple objects or subjects, the model may exhibit a phenomenon known as concept bleeding. This issue manifests as the unintended merge and overlap of distinct visual elements. So, for example, in those images, we can see that we wanted to paint bench white, but instead XL painted the whole room white. Or we wanted to see a lion hugging a giraffe on the TV, but instead they are spawned in the middle of the room. And also, while the model represents a significant advancement over previous iteration of Stable Diffusion, it still encounters difficulties with rendering long and legible text. And that's true. But is it perfect? No. Is it good? Yes. I guess, I mean, at this time. It's still a huge step to some perfect image generation model. And so thanks to the authors.